Hello. Today we are going to talk about the caching basics. In this caching basics, the basic questions comes into the mind that while doing the caching data, how do we know if a piece of data in the cache is there or not? Okay. So that as we know that whenever a program the CPU request a cache or request a data, it will send a requested data address. The requested data address, or that is in terms of we case that cache or cache line address or cache line tag. Cache line tag. It goes to the request goes to the cache first. Cache in this cache, as we have seen in our previous lecture videos, the cache is of the frames like frame 1, frame 2, frame 3. If the data requested data is not there in the cache, then that request forwarded to your main memory, the main memory. In the main memory, as we have seen that there will be a cache lines that every block is known as one block, or we call this as your block or cache line, or simply called the line. We call the line. Okay. So when this data is not there, and here we call the frames. Frames. Frame 1, your frame 2, your frame 3, for example. So when this CPU requests the cache line, request a data in the cache, if it is not there, then that request forwarded to the main memory. From the main memory, if that cache is available, then that will be load into your cache one copy, and from there the it will load into your CPU. This is the general scenario. So from this, these questions arises in the caching, that how do we know that if a piece of data is in the cache? How do we know that whether it is there or not in this cache? Okay, suppose, and that is first question. Second, if it is there in the cache, if the requested data is there in the cache, then how do we find it? Whether the data is in frame 1 or in frame 2 or in frame 3. So how do we know it? Is first question. Another question arises that if the data is not there in the cache, if the data is requested data is not there, or requested cache line is not there in the cache, then how do we get it, or how do we get it from your main memory? So in more detail, these questions gives certain things that if if the if CPU requested the cache line, requested a cache line in the cache, and if that requested cache line is not there in this, then it goes to your main memory, as we said, the main memory cache. Okay, so as we know that in cache there will be frames. So first, if the data block is fetched from, or the block or cache line fetched from the memory, where does it go? Is it goes to the first frame? Is it goes to second frame? Is it goes to third frame? Okay, in which frame it is going to take place? That where does a cache line go when it is fetched from this main memory? So that policy we called it as your cache line placement policy. Cache line placement policy. Okay. Second one is, if this data the block is fetched from the main memory, and that is stored in one cache, one frame here, then how to identify whether this data, the requested data is in frame 1 or in frame 2 or in frame 3, in which frame it is there. That is how to find this cache line in the cache, that we call it as your second policy, that cache line identification policy. Cache line identification policy. So upon the request by CPU, many times, if every time the cache forward that request to your main memory, and from there, every time the block of the caches, suppose they are fetched and they are stored in these frames, suppose, and upon if any additional request given by your CPU, suppose for another block, suppose D, then all the frames in this cache are filled. So then, how to give the placement for this particular cache line which is coming, right? So that we call the cache replacement policy. So said when fetching a cache line into a full cache, then how do we decide what other cache line gets kicked out? That means for to accommodate this cache line D, is it kicked out the B or A or C? Which frame should be kicked out? That is another policy. We call that cache replacement policy. Okay, so while doing the caching, following these three basic mechanisms to solve these questions. Along with that, there is a write strategy that says does any of this differs for read or write operations. That we'll talk about this write strategy in coming lectures. So now comes to the general view of caches. In the general view of caches, as we discussed that, let us see the block diagram of your the frame. The frame is having the cache is having the cache is organized as the frames in the cache, organized as a frames in the cache. So this every field is known as your frame. Okay, so we can call that frame 1, frame 2, frame 3, frame 4, frame 5, and so and so, and so and so. Okay, so every frame is having three fields. Every frame is having three fields. Okay, first field is tag field, second field is status bit field, third field is data field. So let me just design again. This is one frame. Okay, the first frame is the tag. So this tag is the memory address of cache line. Tag is the memory address of your cache line, which is taken from which is fetched from the main memory. This tag will be evaluated based on the cache line which is fetched from the main memory. Second one is your status bit. So this status bit checks whether the data which is there in this data field of your frame is valid or not valid. So that will be decided by this status bit. So this is from here you can see tag is the memory address of currently stored cache line. From where it comes, as we discussed, from main memory. It is divided into represented as every cell is represented as a cache line. For every cache line there will be an address. So that cache line address is known as your tag address. Okay, so this tag is the memory address of your currently stored cache line. And as said that state bits defines valid bits. That means has the valid data in the frame, whatever the current data is there, is that valid or not? That is decided by this valid bits or state bits we call. Second one is if the state bit is invalid, then the entire frame, if this state bit is not valid or invalid, suppose, or not valid, then the entire frame will be erased. Okay, frame will be erased, and then the requested data that will be fetched from your main memory, okay, and that new data we can write it as your data 1 will be written into this frame, and then this status bit, valid bit, will be changed as S1, and based on this cache line address, okay, that address will be updated. Refer as your tag 1. Okay, so this is the frame description, and how it helps to solve the previous three questions. To solve this cache line placement policy, cache line identification policy, cache line replacement policy also. So in this the cache line algorithm or cache line matching algorithm, it will help to do the caching. So what are the basic steps involved in this cache line matching algorithm? Means to find a frames in the cache line, okay, whatever the, if incoming tag means the incoming cache line, your cache line tag, if incoming tag or referenced address, we say, if incoming tag is not equal to the stored tag, in this tag whatever the addresses are there, suppose tag 1, tag 2, tag 3, suppose tag 4 and tag 5, okay, if the incoming tag is not equal to stored tag, then there will be a cache miss occurs, because whatever the CPU is requested, that CPU requested requested access, the CPU requested cache line is not there in this cache, then obviously that request goes to your main memory, to fetch, correct? So then there is a cache miss occurs. So then evict the cache line currently in the frames, evict the cache line if any frame is filled and that is allotted to the next upcoming fetching cache line, then that will be evicted. So evict cache line currently in the frame, then read requested data from the main memory or the higher level of caches and replace with cache line read from the memory or higher level of caches, and upon that return the appropriate word within the cache line. So by following this, let us see an example. Okay, to look at the example, let us consider the page cache line placement policies. In that, one is your direct mapped cache line. At this point, you may not much know about this direct mapped cache line, the cache strategy. So it says that each cache line has a specific or one specific spot in the cache. That means for every cache line, let me briefly explain here. For every cache line in the memory, suppose cache line 0, cache line 1, cache line 2, cache line 3, 4, 5, 6 and 7. In this, when this cache line is fetched from your main memory, when it is going to load in the cache, for every cache line there is a dedicated frame. The dedicated frame 0, suppose frame 1, your frame 2, like that. For 0th cache line, 0th frame will be allotted in direct mapped one. For one cache line, one frame is allotted. For 2 cache line, the next frame is allotted. So that is direct mapping. So in main memory, if its address is 0, then in cache line 0 frame will be allotted. In main memory, if its address is 1, then 1 frame is allotted. Okay, so then to do this mapping, a direct mapper, to do this mapping, there will be a slot mapping we call, or slots mapping, we call it as your slot mapping or tag to cache mapping. So that will be calculated as the address of your main memory, or we call the address of your cache line, that does the modular operation of the size of your cache, size of your cache, size of your cache, size of your cache, size of your cache. Okay, so by doing this, the dedicated frames will be allocated. So that is in directed map, if the cache line is in the cache, if the cache line is in the cache, only one slot for it based on its tag or memory address. No multiple slots will be there. If in the dedicated slot, if any other frame, suppose any other cache lines takes place, that will be kicked out. Okay, so by using this direct mapped cache, in our example, let us try to make the cache line placement, cache line identification and replacement policies. Okay, that makes easy to do this cache line placement. In cache line placement, as just we said, it goes to its one assigned slot based on its tag address. For cache line identification policy, solve that policy, we look at the tag for that one assigned the slot. For cache replacement policy, whatever there in its dedicated slot, if any other cache lines are there, they are simply kicked out. And the write strategies that allocate on the write, or more on write strategies we will discuss later when this topic comes. Okay, so now by keeping this basic knowledge in mind, okay, we'll try to discuss it with an example, the algorithm, cache line matching algorithm. So let us assume that there is a cache with limited size that having only 4 frames, like our the frame 1, frame 2, frame 3, and your frame 4, suppose. Okay, there are only 4 frames. So then what happens when so there are 4 locations in our example in this cache. So as we said, every frame is having 3 fields. One is your tag field, valid data, or status bit, and your data. Okay, so when you are trying to map this from your main memory, as we said, from your main memory, when we are going to trying to map this from main memory, every block or every cache line, for every cache line there is a dedicated, for every cache line there is a dedicated frame here, dedicated frame. So how it is evaluated means that is based on the slot, which slot is assigned to this blocks, which slot is assigned to this block. So how to find out that slot, that tag to cache slot mapping that takes this address, slot is equal to address of modular operation with your code size. Okay, so now what happens, as we are saying that the CPU, the central processing unit, the CPU requests the sequence of data, requests to access the given sequence of memory addresses, that requires the given sequence of memory addresses. Then that memory address will be identified in this cache, and if it is there, then the response will be given. If not there, then that request will be forwarded to your main memory. Okay, so here let us assume that the reference to this main memory address are tags. References to the memory addresses are tags which are requested by your CPU are your 0 means CPU wants to access 0 memory address, 1 memory address access, 2 memory address access, 3 memory address access, 4 memory address access, and so on. So to do that, to the tag to slot to accommodate these, the memory access in the cache. So let us take this as these references as your memory addresses are tags, so which are actually the cache line addresses. Okay, take this. Uh, just a second. Okay, so now let us take this, the memory addresses, the addresses, okay, and then for every cache line there should be a mapping from memory to your cache, right? So that we need to calculate this slot for that memory address which slot is given, for that memory address which slot is given. Let us see that. Okay, then in that slot, whether the data is available or not available. If it is available, as we said, hit. If not available, it said misrate. Okay, hit and misrate. Let us see how it comes initially. So now initially the cache is empty. Initially the cache is empty, so upon any request comes from CPU, it is empty, so no data will be there. So how to find that? The valid state initially it is having all zeros. So upon sending any request by CPU to your cache, it will go and check the first sequence which is given to us is 0. Okay, so in 0 slot, because as we said, direct mapped caching, when CPU sends a zero address request, in the 0th slot it will go and check what is the validity of the data. Here it is saying 0. 0 means invalid data is there, no data is there. That means for 0th address which is requested by your CPU requested 0 address cache line. In that cache line, when in that slot it goes and it calculates the slot that 0 modular 4, it gives the value 0. So in 0 slot it go and check, there is 0 here, so no data is there. That means the data is missing in the cache. Data is missed in the cache. When data is missed in the cache, obviously that request will be forwarded to your cache. To main memory. Right? In the main memory, then that the 0 cache line will be fetched from the main memory, and that will be stored in the data slot. For this 0, the slot is given 0th slot. For this 0 address, the 0 dedicated slot is given. So that is, we consider this data as 1 byte data is fetched from your main memory. So this 1 byte data at the address of the data address of your 0, okay. So once that is retrieved and fetched from the main memory and stored into your data field, then it will go and update the valid bit as 1. Remaining bits are your zeros. Okay, and then the tag is this tag obtained from the cache line. From which cache line the data is? The data for which cache line means here it is for 0 address which is requested 0. So 0 will be updated here. Okay, the next one is the CPU is accessing CPU request for access the cache line 1 at cache line 1. So for cache line 1, again it needs to find out in which slot it is there. Means 1 modular of your 4 that gives 1. Okay, so then it goes to slot 1 now. In slot 1, go and check what is the valid bit. It is 0. That means no data is there. So again the cache line 1 is also missing in the cache. So the request forwarded to your main memory from main memory, that will be retrieved, the data will be retrieved, the cache line retrieved from the address 1, okay, that is 1 byte address, and once it is fetched and loaded into your cache line, then the validity bit, the valid bit, then the valid bit will be updated. The valid bit will be updated. So how it will be initially it is invalid, so now it is going to be updated as 1. And then the tag address will be updated. This is address of your 1, address of your cache line 1, so that will be updated here. Okay, so then, and once it is updated, that updated data will be given back to your CPU for do the execution, for do the the computational performance. So then the next address which is requested by CPU is your 2. So for 2, again it going to calculate the slot, in which slot it is there. So 2 modular of 4, it gives 2. So in the second slot, it go and check the valid status. It is valid status bit, that is your 0. That means no data is there. No data is there means it is missing. It is missing. Okay, so that data is missed. So when data is missing, then it will retrieve that data from your address 2, from your cache line address 2. That is 1 byte of data is retrieved. Correct? So then automatically the valid bit will be updated. From 0, it is going to update the valid bit. The valid bit as 1, and then the address for this cache line, the tag address will be 2. Okay. Similarly, for third, the next axis is the 3. So for third, you do the 3 modular 4, that gives 3. So in the third slot, it go and check the valid bit. It is 0. So that is missing. So the data will be fetched from your main memory and will store into your third slot, which is dedicated slot to it. That is third, that 1 byte of memory. In our example, we are taking this data field as 1 byte, but actually it is in 64 bytes. 64 bytes. The cache line size is 64 bytes. Okay, but for our example, we are just treating as 1 byte. Okay, so once it is updated, then the data, the valid bit will be updated from invalid to your valid, from invalid to your valid as 1, and then the tag address will be updated as your 3, because the cache line address is 3, right? So the next one is 4. CPU requests the 4 memory access or cache line. So that is 4. For that 4, what is the dedicated slot means? The tag to cache slot mapping gives as your 4 modular 4, that is 0. Okay, in this case also it is missing. Okay, it's 0. So in the 0th slot, it go and check the valid bit is 1. The valid bit is 1. When the valid bit means requested tag, valid bit is 1, then it assumes that the data which is there in this is valid. Correct? In that case, when it says that the valid is the data which is there in this frame 1 is valid, frame 0 is valid, in that case the tag, we call this 0 as stored tag, right? This stored tag compares with the incoming address tag. That is what mentioned in the algorithm. If the incoming tag is not equal to stored tag, then there is a cache miss. When cache miss occurs, then the new data must be fetched from the main memory, right? So in this case, now see, the stored tag is 0. whether it is equal to the incoming tag. Incoming tag is 4. Incoming tag is 4. Is it equal means? Is it equal means? It is not equal. When it is not equal, the stored tag and incoming tag, when both are not equal, that means though the valid bit is 1, the data is not requested data. So in that case, what happens? The frame must be evicted. The frame must be evicted. So when it is not equal, then the everything which is there in that frame 0, that will be evicted and make free to accommodate the data which is requested for that dedicated field. So here it is not equal, so the data is missing. So then that cache line must be fetched from your main memory. So that is 1 byte fetched from your main memory of your cache line address 4. Cache line address 4 at tag 4, and then make this bit as valid again, and then update the tag address as your 4, because the cache line address is 4. Okay. Next, 5. Okay. So when CPU requests this address 5 cache line, then it goes and check its tag to the cache slot mapping. In that 5 modular 4 is equal to your 1. In the one slot, valid bit is 1. Okay. So that means the data is valid. In that case, once valid bit is 1, then the comparison takes place. What's comparison? The stored tag value compared with the incoming tag. So here at one slot, the tag value is 1 and 1, and the incoming tag is 5. Whether this is equal or not means it is not equal. They are not equal. They are not equal means actual data is missing in the cache. Actual data is missing in the class. When actual data is missing in the cache, then the frame will be evicting, or the data will be erased from this frame. To accommodate the cache line which is fetching from the main memory. So which cache line? It is fetching the cache line of your 5, that is 1 byte in size in our example. Then set this valid bit as 1 and update the tag address as 5. Okay. So, and once it is updated, then that updated cache line 5 will be given to your CPU for its execution purpose. And then the next request CPU is given is 2. So for 2, it goes and check the slot, in which slot cache line 2 is there. That is the cache line placement policy. So in 2 modular of your 4, you will get 2. So in the second slot, the valid bit is 1. So then it is going to compare the incoming address and your existing tag address, stored tag address, that is 2 equal to 2. So it is matching. That means the data which is there in this data field is valid. So here it gives that hit, because it is not going to fetch from the memory. It is hit now. Okay. So then when it is hit, then the frame keeps as it is, because the cache line which is dedicated for it, for cache line 2, the slot which is dedicated to is correct one. So there is no eviction here. Okay. And next one is 3. So for 3, it finds its dedicated cache slot from this tag. How it finds? 3 modular of your 4, that gives 3. So in third slot, it is going to check what is the valid bit, status bit, that is 1. That means valid. When it is valid, then the incoming tag or incoming address is compared with the stored address, that is 3. So it becomes in this comparison 3 equals to 3, so it is matching, so it comes as your hit, and this data will be given to your CPU. Then the another one is uh, the last address is your 7. So in 7, in this address slot, hit or miss. Okay. So the address is 7. For this 7, it need to mapping this tag to cache slot or the cache placement policy, that 7 modular of your 4, 7 modular of your 4. So that is your 3. That is your 3, your hit or miss. Okay. So in slot 3, it says that there is a valid data. Then it go and compare the stored tag with the incoming tag. That is 3 equal to 7 or not. Obviously, it is not. In that case, it says that it is missing. It is missing. When it is missed, then it will be erase the existing frame, because now this frame is dedicated for the cache line 7. So they erase this data from this frame, and then it is going to store the data, fetch the cache line 7 from your main memory, and then set the valid bit as 1 and tag bit as your 7. So this is the way of caching when the CPUs request the sequence of references to this memory address or tags. Then how it is going to do the cache placement in this cache, as we saw that cache placement done based on its dedicated slot. Okay, and in their dedicated slot, if any other frames are took place, then the replacement take place at this slot 0, slot 1 and slot 3 in our example. So from this you can find there are 1 2 3 4 5 6 7 8 9, total 9 tags were there. So 9 references were there, total 9 references were there. From there we can calculate the hit rate, means number of hits. The hit rate is given that number of hits divided by number of references, and similarly your miss rate calculated the number of miss divided by references, right? So from here, how do you calculate your hit rate? Your hit rate is equal to number of hits in our example is 1 and 2. So 2 and divided by how many references are there, are the memory addresses requested by CPU, means 9. Okay. Similarly, your miss rate, calculate number of misses, that is 1 2 3 4 5 6 7 misses. 7 miss divided by total number of. So this gives the hit rate and miss rate of the caching. Okay. So this is in this example is clearly given in the next coming few slides that follows the same procedure. Okay. So this empty, initially the cache line is empty. So then it calculates the slot for the first request, that is 0. Read data at address 0. That 0 was, slot 0 is invalid initially because that was 0. So then the data is not there in the cache, so the cache miss occurred. So read data from memory and store data in this slot. So we read data and store data in this slot which is allocated to this, the dedicated slot is 0, and then set this valid bit as 1 and set the tag address is 0. Similarly for the read address 1, it happens initially, the valid bit is 0 here. So that means that cache read data at address 1 is invalid. So that will be fetched from your main memory and placed in its slot. And this process continued as we just explained in the previous. For your reference, for your clear understanding, these slides are given. You please follow this one. Okay. So then from this, we have seen the cache performance equation. In the cache performance equation, as we just find out that miss rate and hit rate. So the percentage of data accessed or cache misses, and hit rate means the percentage of data accessed or cache hits, right? So in our example, in the slide 28, where we started our example, there are 9 access that we have seen: 0, address, 1 address, 2, 3, 4, 5, 2, 3, and 7, right? Total 9, the accesses in total, and 2 of them are hits. 2 of them are hits. That is, these 2 are hits. All the remaining are your misses. So the hit rate is, then we just find out that 2 divided by 9, that is 22.2%. 22.2%, and the miss rate is 7 divided by 9, that is 77.9%. 77.9%. So from this, the average memory access time, how to calculate the average memory access time or the performance of your CPU equation. This average memory access time is actually a weighted average. It is actually a weighted average. So the weighted average, okay. So this weighted average memory access time is used to represent the average memory latency. Average memory latency for a series of memory access. For a series of memory access, that is what we have observed now. That is the series of memory access 0, 1, 2, 3, 4, 5, 2, 3, and 7 series of memory access. It clubs how much time taken for this 0 memory access, 1 memory access, 2 memory access, and so on. So that is named as your AMAT, average memory access time. So this AMAT is calculated as the latency hit, the time taken for your hit, and its hit rate for this series of memory. Okay. Similarly, how many times missing, latency miss with miss rates. So latency miss means, we have seen in the total latency miss means how it is happening. If you recall our previous lecture series, when CPU request given to your cache line, in the cache line, if it is not there, if the requested data is not there, that means in this cache, if it is not there, that means it is miss, right? Once it is missed, then that request is forwarded to your main memory, and in the main memory data is located. In the main memory data will be located, and that one will be passed back to this one. So this phenomena, we call this as your miss penalty. So your miss latency means the time up to this hit, latency for hit plus the miss penalty. So that is the latency miss is typically known as your latency hit time plus the miss penalty time. So for our example, in our previous example, you just assume that the hit latency time is 1 nanosecond. The hit latency, the time which takes from here to here, is 1 nanosecond, and the miss penalty time, that is the process of sending request here and finding that and given that you are 100 nanoseconds. Assume 1 nanosecond for this, latency hit, and 100 nanoseconds for this miss penalty. Then the average memory access time for these example, for our example, this one, for memory accessing this series of memories, then will be calculated that the latency hit rate the latency hit multiplied with the hit rate or rate of hit plus your latency miss and miss rate. So latency miss means how we are calculating the hit plus your miss penalty. Okay. So now this latency hit is 1 nanosecond multiplied by your hit rate. Hit rate which we calculated here is 22.2%, 2% plus your this latency miss means latency hit plus your miss penalty. This is your latency hit plus miss penalty. Okay, so latency hit means again the 1 nanosecond, and miss penalty as we are given in the question that 100 nanoseconds multiplied with rate of miss which we calculated, that is 77.8. So that will give the average memory access time for the given series of memories is 78.8 nanoseconds. 78.8 nanoseconds. So this is very important for your assignment purpose also. So this is the way of calculating average memory access time. Average memory access time. Then the memory time and execution time. What is the memory time and execution time? Okay, these are two separate entities. In general, an application's execution time can be partitioned into your memory access time and computational time. Memory access time and computational time. So cache misses typically cause the pipeline stalls, because when cache is missing, then that request goes to your main memory. When the data is fetching from main memory, during that time your cache will be, your CPU is stalled. So which constitute the majority of the memory access time, which constitute when cache miss happens, then that constitute to the majority of your memory access time. So therefore we can roughly decompose the execution time into the execution time of any application into the time computational time and the memory access time. Computational time and memory access time. So computational time is common, that will not change. But when it goes to your memory access time, if in the memory access time, that means cache miss is happening. So the main memory is accessed. During the main memory access, your CPU will be stalled. Your CPU stops until it get the data from the main memory to cache to your CPU. So that we call this as the latency miss time. Latency miss time, because in CPU it is not there. So there is a latency miss time. So that we call latency miss with miss rate. Latency miss with miss rate. Okay. So that is the memory time and the execution time. So once the latency miss and miss rate is calculated, that will be added to the computational time, then that will give the total of your execution time of your application. So this memory time and execution time, in this, for a better accuracy, it is also better to consider read and write accesses separately in the previous equation. In this read and write separately in this equation. So strictly speaking, the execution time here is just the CPU time, and actual execution time also includes the input output wait time and OS scheduling time. But in our example, we just consider only the CPU time only for our example. Okay. So then hit latency and miss rate summary together. If you see that miss latency is mostly determined. Why? Miss latency means this miss latency depends upon the speed of your DRAM. Speed of your DRAM. In the very beginning of this lecture, this topic, we have seen that DRAM growth is 7% per year. So the latency of data path from CPU to DRAM, that gives the miss latency. Another one is your hit latency is mostly determined by the latency of the data path from CPU to cache only. CPU to cache only. Okay, as we have seen the CPU request the data and request the cache line in the cache If it is there, if the data is there, then it is simply a head part, and that will immediately respond, load it to CPU. So the size of the cache, if it is larger caches, then there will be a slower in the latency. If these smaller caches, then the latency is, the less latency is there. So the time it takes to compare the tags, that will take time for this the actual to increase or decrease this latency. So then miss rate is just the major cache optimization metric. So most cache optimization aim at reducing miss rates, since the miss latency is much higher than the hit latency. So cache misses dominate the memory access time. Therefore, reducing the miss rate can significantly help memory performance. So some the cache optimizations, however, may reduce the miss rates but increase cache latency. They may reduce this miss rate but increase the cache latency. Example, use the bigger caches. Okay, so this, I would like to stop the session.